Alright, we're going to do some U-substitution. Alright, we're asked to integrate. So identifying the inside function, if u is this trinomial, the derivative 2x plus 3 is present as the factor here. So we're going to let u be the quadratic, the inside function on the power of 8. So du is 2x plus 3 dx. Okay, it doesn't look like I need to bring anything in, but this 9 I'm going to pull out front just to kind of clean it up. When I pull 9 out front, this is going to be left to be u to the 8th power, and then all of this will be replaced with du. Just the reverse power rule. Increase the exponent to 9, divide by 9. Don't forget the plus c. Noticing we can cancel the two 9s. So I'll just be left with u to the 9th, and I'm going to replace u with what we designated it to be in the beginning. You can always check your work by differentiating. You can differentiate this answer to see if you get back to what we had here in the integrand. Alright, kind of paying attention to u, kind of studying it for a moment. I have sine squared of 3x and cosine of 3x. It might be helpful to pull that square off this trig function. Sometimes that's helpful to see, then how to proceed. Alright, so when you have a power, you might want to kind of explore the option of letting u be the inside function on that power, and if the derivative produces the other factor, then that's a good way to proceed. And that's what happens here. Using the chain rule, the derivative of sine is cosine. Leave 3x alone. And then multiply by 3, so I'll put it up front, and I need the dx here. So it looks like to go to u integral, I need to bring in a 3 and pull out a 1/3. So this is all going to be your u squared, and then all of that will be your du, which allows you to integrate. Reverse power rule. A little bit of cleanup and replacing u. If you want to pull the 3 back on the trig function as the power, that's fine. If you want to stack it as a fraction with 9 being the denominator, that's fine too. Alright, problem 3. Studying the integrand, noticing we have an e. Oftentimes one of the first things to kind of explore is that u would be your exponent. It should work out fine. Since the exponent is linear, the derivative is going to be a constant, and we can bring in a constant. So we see we need to bring in a 3 and pull out a 1/3. So we end up with 1/3 integral e to the u, and then all of this will be our du. Antiderivative is just e to the u. You just check your work by differentiating. All right, example 4. Okay, again, we have another e present in the integrand, so why not at least first explore u being the exponent on e. So if u is tangent, then the derivative would be secant squared. Well, I don't see a secant squared, but if you remember from pre-cal, 1 over cosine squared can be rewritten as secant squared, since those two functions are reciprocals. So I think that's going to be the right way to proceed, is to let u be the exponent on e. Alright, then coming over here, maybe doing a little rewrite on this integrand. Okay, think of this as 1 over cosine squared, so I'll pull that up and make it secant squared. Okay, noticing that our derivative is secant squared, I don't need to bring in anything. I'm going to go to the u integral, so e to the u du. Antiderivative is e to the u plus c. Right, example 5. Okay, here we have e present in both the numerator and denominator. If we went forward with letting u be the exponent x, well, that derivative is 1, and that's not going to take care of this complicated looking integrand. So we need to come up with another thought about how to proceed. All right, let's let u be the entire denominator. The derivative of which is just e to the x dx. And that gives us what's in the numerator. So I'm going to pull the denominator up with a -1 exponent. Okay, we still have e to the x dx. And then it's just a better visual of what we need to do. All right, we're going to let the inside function here on the exponent of -1 be our u. And then I don't need to bring in anything. So this becomes u to the -1 du. And we integrate that back to the natural log. Natural log absolute value of u plus c. So we've had a variety of integration rules. We've had the reverse power rule, we've had the e rule, and now the natural log rule. Okay, now noticing number 6, we're given a derivative and we're asked, well, what is y? That implies that we're going to have to integrate. This function right here is just in terms of x. So it's not like we really have to separate the variables, put y's on one side and x's on the other, because it's already just in terms of x. Okay, but I'm just going to go ahead. It's not wrong to separate the variables. I'm going to pull the dx to the other side. All right, and then once we have done that, we can bring in the integral symbol. Antiderivative here of 1 goes back to y. We're going to have to do a U-substitution. Okay, if u is 2x and du is 2dx, we're going to need to bring in a 2 and pull out a 1/2. So we're going to have cosine u du. And that's going to integrate back to sine of u plus c. All right, just a review of various U-substitution problems.